Imagine a material that's not just strong, but 10 times stronger than its regular self, and yet it bends without breaking. Sounds like something straight out of a superhero movie, right? But engineers actually did it with a special cobalt-aluminum alloy. This isn't some magic trick, it's a real scientific breakthrough, and the secret behind this incredibly robust, yet surprisingly flexible material lies in something unbelievably small. We're talking about manipulating matter at the nanoscale. Prepare to have your mind blown. For ages, we've had a tough choice with metals. Make them super strong, and they usually become brittle, like glass, or make them flexible, and they're often not very strong. It's a fundamental trade-off that has limited what we can build, from aircraft to medical devices. To understand this, think of a metal like a wall made of countless tiny bricks. Each brick is a grain of metal. When you push or pull on it, tiny defects called dislocations move around these grains. Too many dislocations piling up at a grain boundary, and snap, the material breaks. These dislocations are key to how metals deform. In traditional strong metals, engineers often try to make these grains smaller to block dislocations. But while this makes the metal stiff and hard, it typically also makes it prone to sudden catastrophic fracture. It's like having a very rigid but brittle wall. This is where nanoscale engineering comes in. Instead of just making grains small, imagine controlling the structure at a level 1,000 times smaller than a human hair. We're talking about individual atoms and tiny clusters of atoms, arranging them with incredible precision. Engineers focused on a specific alloy, cobalt and aluminum. Individually, they're useful, but how do you combine them to break that strength-flexibility dilemma? The answer wasn't in adding more of one or the other, but in how they meticulously arranged them at the atomic level. Their breakthrough wasn't to just mix them, it was to create super tiny, layered structures within the alloy itself. Imagine incredibly thin sheets, almost like microscopic pages in a book, made of different cobalt and aluminum compounds, stacked together, each only a few nanometers thick. These nanometer-thick layers act like super tough internal barriers. When dislocations, those tiny defects, try to move through the material, they hit these layers and get stuck. It's like creating an intricate maze where the defects can't find their way out, making the material incredibly resistant to breaking. But here's the mind-blowing part, the unexpected twist. Usually, trapping dislocations makes things brittle, so how did this material become flexible? The secret is that these layered structures, when stressed, don't just stop defects, they undergo an incredible internal transformation. When enough force is applied, specific nanoscale regions within the alloy undergo a stress-induced phase transformation. Imagine this as a controlled internal rearrangement of atoms into a new crystal structure. This transformation effectively dissipates mechanical energy, enabling the material to deform significantly and resist the formation of brittle cracks. As it deforms, this material dynamically reconfigures at a microscopic level. This involves twinning and phase transformations that act as internal shock absorbers, distributing stress and preventing localized failure. That's precisely why it's not just 10 times stronger, but also remarkably ductile and flexible. To put that 10 times strength into perspective, imagine a regular aluminum beam supporting a small car. This new cobalt-aluminum alloy could support 10 cars or even a small truck with the same size beam and bend instead of snapping. That's a truly monumental leap in material science. This isn't just lab magic, it has profound real-world implications. Materials like this could revolutionize everything from aerospace to medical implants. Lighter, stronger aircraft components mean more fuel efficiency and safer flights. More durable, flexible implants mean better patient outcomes and longer-lasting devices. This nanoscale triumph shows us that sometimes the biggest breakthroughs come from thinking about the smallest things. By meticulously manipulating matter at the atomic level, engineers are literally rewriting the rules of material science, giving us properties we once thought impossible. The potential is immense. Imagine cars that are safer and lighter, buildings that can withstand massive stresses, or even new energy technologies that rely on ultra-strong, flexible components. All thanks to arranging atoms with such precision to create materials we once only dreamed of. What other incredible materials do you think nanoscale engineering could create? Let me know your ideas in the comments below. If you found this dive into tiny structures and huge breakthroughs fascinating, hit that like button and subscribe for more amazing engineering stories. And for another mind-bending material, check out our previous video on self-healing concrete right here. Thanks for watching, and I'll see you in the next one.